Well, it's official, folks. Looks like we can get started. Welcome back, everyone. Well, what did we do last time? We were mostly just starting chapter 19. We went through some new data types, how to calculate a brand new statistic, essential limit theorem, but we've yet to actually do any statistical methods in chapter 19. We're getting pretty close to it, though. I have a due date for this chapter, assignment number 9, now Monday, but that one might be pushed to a Wednesday, just in case we take a little extra time to finish chapter 19. But what I would encourage folks to do is, as far as assignments 7, 8, and 9 go, they are extremely pivotal because they correspond to these chapters. And honestly, I think the best way to study for an exam like this one is truly it's the homework. Getting your feedback back on your homework, seeing what you might have made a mistake on. Those things are really huge for studying for exams. So probably the best thing you can do to be prepared is try to get assignment number 9 done as soon as possible. Even if the due date is pushed on Wednesday, if you get it to me on Monday, my goal is to try to grade it as fast as I can and get it back to you before the actual day of the exam. So you'll get some feedback on that 9th assignment. So that was my major thing to get out. After we finish chapter 19, we already have 3 major statistical methods on the table, and each one of our method can be either a hypothesis test analysis, a confidence interval analysis, or both at the same time. But really with 3 big methods already, in chapter 20 we'll have 4, then 5, 6, and so on. This becomes the more important work we need to do. We need to know how to differentiate when to select the right method based on the right type of data. And pretty much the major thing that does this for us is we go back to chapter 1 and we just say, what are the variables? Are they quantitative? Are they categorical? If they are categorical, what are their categories? All of that work at the start of the class was really to help us choose the statistical method. So we'll start paying more attention to this document as we get more and more methods. And this document is, in a certain sense, like the review for the final exam. The final exam is a take-home exam, and I'm not going to give you tons of problems, but the problems are randomly sorted, and it's up to us to choose the method. So here's where we'll practice doing that same kind of thing. Aside from the other announcements, we have our exam 3, which is going to be Monday of next week. And we're just going to repeat exactly what we did for exams 1 and 2. Well, 2 was a take-home exam due to the snow event, but you know what I mean in spirit. We'll try to redo that. It'll be a real exam held in a classroom or in the Pocatello Testing Center. And just as a reminder how all that goes is, for me, I need to get this exam written by Wednesday or Thursday of this week, so either the 3rd or the 4th. Then I send it out to the Pocatello Testing Center with a roster. And then once they have that in their schedule, I'll email you folks to let you know you're ready to call them to schedule your exam. And I hope to have that done around Thursdays when I'll be emailing you to let you know. Any questions about that so far, folks? The exam or the other announcements? Yeah.
Just, I guess, reading that final bullet there. So for this upcoming exam, can I use like my TIA, I think it's a TIA 80?
I'd be okay with that, yeah. I noticed that there was a lot of confusion on the very first exam, so I'm glad you mentioned that. I looked at the way I put the wording on the syllabus and what I actually said on the exam 1. I seem to indicate to people that you need to use specifically these 2 calculators. That's what I'm doing in my other classes because the math department forces me to, like college algebra, trigonometry. And I think I just carried that mentality to our class, but it's less of a worry for us. So yeah, if you have a different scientific calculator that you're just used to using, go ahead and use it. I'll be completely okay with that on the 3rd exam. And again, sorry for the confusion about that. Other questions at the moment? Okay, other things that are going to happen as we go across the weekend is, well, one thing I should mention is definitely check out the exam 3 formula sheet. As you're doing your homework problems, studying for the exam, having this just available in front of you is going to orient you where all the interesting bits are and how to apply every bit of one of these things. If you saw this formula sheet for the very first time on the day of the exam, that is a disadvantage for sure, I'd say. So this will be the last sheet on the exam. And notice what's there. You have methods for the confidence intervals, the test statistic, that kind of stuff. If I ask you to calculate degrees of freedom, I felt like this is a good formula to throw on there. There's nothing about checking conditions, but I'm not going to emphasize on exam 3 condition checking as much. I feel like that's more careful work that you'd want to do on a homework setting where you can really look at the data, look at box plots, histograms, those kinds of things, and make careful considerations. So our exam is going to be more apply these kinds of things to construct a confidence interval, a test statistic, and analyze conclusions like interpret a confidence interval, interpret a p-value to see whether you reject or fail to reject a null hypothesis, and that kind of stuff. So just like exams 1 and 2, exam 3 is really going to be mostly a concept question kind of exam. I think that's my major spiel so far for the announcements. Other questions or comments so far, folks? Okay, I'll probably remind us again, but once we are on Wednesday's class, getting ready for the weekend, we'll have our next review day on the 8th, and it's going to be student directed just as normal. So if you have, and hopefully no snow day, so if you have questions that you definitely want to take a look at and have addressed, whether they're on any of these documents or elsewhere, definitely send them to me when we start class, and we'll do our review in a student directed way as before. I have these sample exam 3 problems, which are just the lecture notes written as more of an exam question type thing. And I'll also be including an additional file like we saw before, just in case we want more problems to take a look at. But that's kind of it for the announcements. We look even further into the schedule. After the 3rd exam, we'll have one normal week to just do as many statistical methods as we can on this week. We're probably going to get into chapter 20, 21 if we have time. Then on this week here, Monday we'll be finishing off whatever we left off on Wednesday, and then we'll be transferring over to just reviewing for the final exam. And then on Wednesday of this week, at the end of class, that's when the final exam will be made visible to everyone, and it'll be a 1-week turnaround on the due date. So it'll be due Wednesday, May 1st. So we're pretty much there, folks. Let's count them. We've got 1, 2, 3, 4, 5 weeks if you count finals week as well. So just about there.
Good.
Congratulations, I agree. It's a lot of work to get through this class sometimes, and I know this is not necessarily your only class, so it's a lot of time that you have to pay attention to with everything going on. But other questions at all, folks, before we go back to chapter 19? Okay, well, let's take a look at about where we left off. I skipped to the central limit theorem since everything up above in the document is more just tying things together, how we transition from the old central limit theorem to this new one, how to calculate the statistic, identify a parameter. But now that we have the central limit theorem on the table, this is the basis for essentially all of our methods. This location right here is the exact standard deviation for the sampling distribution of p hat, the statistic right here, its sample proportion of successes. But unless you're doing a hypothesis test, you can't actually calculate this. So what we do instead is we make the point estimate right here, and that's what gets us to our new standard error. We just go to the standard deviation right here and put in our estimate, p hat, into these 2 positions. So with that new standard error in play, you'll notice that a lot of our confidence intervals pretty much go like this. A point estimate, add and subtract some critical number, and then multiply by some standard error. So if you can describe the standard error, you pretty much have, well, the entire confidence interval. It'll go like this. P hat, right here is the point estimate. We're using the same critical number as before in chapter 14, so way back. Z star is the right distribution here, using the normal distribution rather. And that's the standard error once again. We'll take another look at these conditions once we get to that portion of the problem. But another thing that's kind of beneficial for us is if I give you some non-standard confidence that you need to calculate, like a 97% confidence interval, that's weird, but you can make it happen through this identity right here, or this formula. Or these are the standard levels of confidence that we typically see, and Z star is fixed for all those values in this chapter. Since we're using the normal distribution, we don't have things that change based off the sample size, like in chapters 18 and 19. So that's our entire interval. Now let's go and practice it down below. We took a really quick look at this pretty old data, but this is nice data to practice with. We're looking at the evaluation of the policy of vaccination for whooping cough, and they're counting the adverse reactions in 339 infants. So it looks like we have a sample size of 339. What they want to study in this problem is those adverse reactions, wherever they were, mild or severe. They don't specify in this short write-up, but they did note that adverse reactions happen in 69 infants altogether. So that's the thing we're trying to study, which is why we're calling it the success, as morbid as that seems. The variable for successes is typically in uppercase. I'll write this as 69 and just put a successes by it just to emphasize. I think we can get rid of that note there. And we'll look at that confidence interval when we get to that point of the problem. So this is the setup so far. And when we go to describe this thing, the unknown parameter has now changed. We're not trying to calculate a single mean, mu, or multiple means, mu1, mu2. We're looking into a parameter p. So I'll describe the parameter in this way. And this is anytime you have a categorical variable. So p is going to be the true proportion. In place where I wrote proportion, you're fine to just use percentage if you prefer. And I'll often use percent right here if it's a practical interpretation. So P will be the true proportion of successes, whatever successes were. But when we find the successes, we just go backwards into the problem and look at this portion right here. It says reactions for short, but that's adverse reactions. So we'll say P is the true proportion of adverse reactions to the whooping cough vaccine in infants. Who knows what those adverse reactions were, but I actually Googled whooping cough mistakenly. I don't recommend it. That's a pretty terrible thing to go through. So, but whatever those adverse reactions were, it was probably better than the disease. But that's a parameter. Any questions at all, folks, on part A? Okay, just like if we were describing a parameter that goes like this, mu, I'll delete this in a moment just for, this is just a quick note. Mu is often going to start as it equals the true mean of something. But the one thing that we have to state whenever we're indicating this parameter is that the fact that it's the mean, or you could have said average just as well, average of whatever it happened to be. Over here, if you put the symbol mu, that's not as big of a worry. I'd probably just put a slash there and say should be p. But we have to say somewhere the fact that we're dealing with a proportion, this problem, just like over here, we had to mention mean. So watch out for this right here. It's easy to accidentally say the true mean when you meant proportion or percentage. So going down next, we're going to check out not the typical thing we call robustness conditions, but it really is a form of robustness. Just like the one sample, the two sample t-distribution, sample sizes had to be large enough to overcome whatever skew we saw in the actual sample data. But these data are categorical. We don't have the same notion of skew versus symmetric. So instead, we're just wondering, is the sample size large enough to use this, the large sample confidence interval? And the major thing we need is at least 15 successes and at least 15 failures in the sample. If it was a hypothesis test, all that works totally different. So we'll make a big deal when that changes. When you go to write out this conclusion, do indicate how many successes you found. So we'll say here, since there are 69, and this always looks funny, but I'm putting this next portion down just because it's the benchmark we had to exceed. 69 is definitely greater than or equal to 15. Successes. And to get the failures, just go to the total sample size, 339, subtract the successes. This one's 270, so easily meets the benchmark, greater than or equal to 15. Failures. The sample size. Is large enough. So that takes place of robustness. And if the sample size was too small, we could have failed if just one of these conditions here or right here didn't succeed. So we have to have greater than or equal to 15 on both successes and failures. We still have more to say, but any questions, folks, so far? Okay, again, don't forget to include the actual counts here and here, just so that I know that you know what the successes and failures were in that given problem. And it's also more important than it seems because hypothesis testing changes all this around, and we don't want it to be too foggy in our minds when we add the next type of analysis. Other things we can look at is we're looking for randomization, and it says 339 infants who received their first injection to the vaccine. No information about randomization at all, but this was a serious study published in The Lancet, sure, in 1974. I bet we could find out what their methods were to see if they did use randomization, but you never have to go that far in these kinds of problems. What I would say at this point of the analysis is that provided these data came from a random sample, the conditions are met. And there's one condition we didn't actually directly touch. It was the one about the actual sample size at 339 infants could not exceed 10% of the total population size, which would have been all infants. That seems very plausible. We're only looking at 339 when we're considering all infants. We're looking into a huge, huge number. So the condition I'm thinking about is this one up here. Let's take another look at it. This one is always safe to skip since it will be, well, I don't think these problems come up at all in our class, and they do come up in real life. This is something to think about, but for us and our problems that we're working on, good one to think about, but not something you have to directly comment on or do any extra research to determine if it's plausible that condition passed. So we're mostly checking this one. Same with chapters 18 and 19 with the robustness conditions. We were looking at the sample size was large enough to overcome skew. This is the major thing that we can do as outsiders looking into a study that was already concluded. But anything we can say is related to randomness is definitely worthy of saying one way or another. It'll be the same kind of theme for every one of our conditions we go through. Now, next thing we'll do is run through the actual mathematical portions, the formulas and such, and construct our confidence interval. But any questions, folks, with this early stage of the analysis? Okay, well, this is the fun part. When it says sample proportion successes, now we're going to the statistic. We know it must be because it said sample. The statistic that estimates lowercase p is this, p hat. Just like with mu or x bar, if you wrote this on your paper, that's completely fine. If you wrote p hat, I'm absolutely fine with that as well. And if you want to actually type it out, the way it goes on your keyboard would be hit Alt plus. Oh, that was not Alt plus. Let me try again here. I think I did Windows plus. There we go, that's the magnifier. Hit Alt plus, and then if you type P, this slash in that direction, HAT, space once, space again to center it, then you've got your P hat. I only mention this since some people do want to typeset their things in this way, but you do not have to, only if you're interested in it. But that's our statistic P hat. And the formula is always this way. X divide by N. So we just go to the number of successes, 69. Because it's a proportion of successes, we divide by the total sample size, 339. And you could estimate this if you like. I'd say go for 5 or 6 decimal places for significant digits, but I'll leave it just like this and throw it into the calculator in that format. So we've got it, folks. That's the sample proportion of successes. Next thing we need is standard error. Standard error is going to be based off this right here. And if this was a real exam 3 question, we should anticipate it for a real exam 3 question. Good strategy is just to write down the formula first. So SE, and if you want to be specific which standard error, put SE of P hat is square root P hat, 1 minus P hat, divide by N. So there's our formula. This gives you partial credit already, just knowing the right standard error that has to be selected. Then from here, let me make this a little bit longer. Here's what it should look like right before going to the calculator, where you would get a massive amount of partial credit, even if you made a mistake in the calculator. It'll go 69, 339 multiplied by 1 minus 69, 339. Kind of ugly the way it goes in, but I guess it's faster than a decimal expansion, sort of. Then divide by 339. And now our task is just to jam that into a calculator. So order of operations will just be go left to right, top to bottom. First call SQRT, 69339 times, then 1 minus 69339, then divide by 339. And it should be just fine as far as order of operations go in your calculators, just like that. So I get a standard error of 0.02187 if we're rounding to that digit. Let me double check those digits. It's still just a Monday. 0.02187. Okay, I think that looks all right. How's that working out for folks so far? Are we all getting about the same quantity here? Okay, well, next thing we're going to go for is a 95% confidence interval. And that means we have a lot of great options here. Some people might go like this, negative Q norm, 1 minus 0.95, divide by 2. And you could use this number right here. Or if you decide to use these numbers, that's always completely fine as well. I'll use this one right here, 1.9600 for 95% confidence. I start by saying for C equals 0.95, this implies that the critical number Z star would be equal to 1.9600. So now the formula for the confidence interval will go P hat, add or subtract the critical number Z star multiplied by the standard error of P hat. So just about there. Now we're just doing a bunch of substitutions. For the first term, 69/339, which we're adding, subtracting to 1.9600. Now we're at the standard error portion where that's going to multiply that whole number right there, 0.02187. This kind of looks funny when we say standard error P hat, but think of the of P hat as this is just one symbol altogether that's much like function notation. So you're not putting this number times P hat. This is all just the whole number, 0.02187. So that's what the interval looks like. Next step is just to, again, jam it back into the calculator. It'll be 69/339 minus 1.9600 times 0.02187. Provided I didn't miskey anything, our lower end is 0.1607 if we round to 4 decimal places. Already forgot, let me try again. 0.1607 is less than, and now our statistic P, or excuse me, our parameter P comes back in the picture. That's the thing where we're estimating by the confidence interval. So let's use blue just to emphasize. And then hit up arrow or second answer on your calculator, depending on your calculator. Call the last line, and this is the upper end, 0.2464. Now, you can recall these are percentages, so you could say P as a percentage is between now 16.07% and 24.64%. Well, we did it, folks. That's our confidence interval. All we have to do is just another practical interpretation of what we produced, but all those go very remarkably similarly. Any questions at all so far, folks, to getting those low values? Okay, well, our parameter was pretty fast to state, so we can probably just come right down here and write out, double checking the level of confidence. We have 95% confidence that the major thing of interest is P. It's a proportion, but I'll call it a percentage right here and say the true percentage of infants that have adverse reactions to the whooping cough So we took our P, and now we just say is between 16.07 and 24.64%. And that concludes the analysis. Looks like a pretty high percentage on the upper end, not terribly bad on the lower end. And that true percentage is somewhere in the middle, or not necessarily in the middle, but somewhere inside of there, provided our method actually worked. And how often does it work? About 95% of the time since we selected that confidence level. And that's accurate because the number of successes and number of failures both exceed 15. Just one of those fail, that's what goes wrong really quickly. If you said 95% confidence, it might have really been like 88% confidence if one of those conditions failed. Well, any last questions at all, folks, with analyzing our first analysis of categorical data? Okay, definitely riveting stuff. But we did mention one thing that is kind of nasty about this. It is a large sample confidence interval, and because we have to exceed 15 on successes and failures, the minimum sample size is 30. That doesn't sound terrible on its own, but there are things considered rare events, say rare diseases, rare outcomes of any kind, where the actual condition right here does fail. We're not looking into any of those fringe kinds of problems, but if that does fail, we have an issue. But on the other hand, maybe the population size is large. It's just really hard to get a success. A success could be just very, very rare. If that's the case, to get above 15 successes, the sample size right here might have to be tremendously large. So large that no one could actually afford to do the study. Maybe the government doesn't even want to invest in it. Whenever that happens, well, we can't use a large sample confidence interval. And there are other procedures. There's the so-called Fisher-Exact test, where we're not using normality to try to approximate p-values or critical numbers, instead of using the binomial distribution. But another easy method for us is the +4 method. The remark here is essentially our issues we have with the large sample confidence interval. And here's how it's resolved. The +4 estimate of P. It's written out this way. You're dealing with a +4 estimate if you have a P that's read as a tilde as your estimator. So that one can be typed out as P, and then I think it's slash. You just literally write in tilde to get your tilde, and then space it again to center it. Or if you're just typing it out, it's fine to just type it out as P tilde. Everyone would know what you meant if you wrote it out that way. So somehow, some way, this +4 estimate of P gives us some accuracy when the ordinary conditions, number of successes in the sample right here, number of failures in the sample right here, do not both hold. So if we can't get away with that, this estimator is nice because your sample size has to be at minimum 10, and your confidence at minimum 90. This one is mainly here just for completeness because we usually never give a confidence interval below 90%. So in a certain sense, this is our small size confidence interval. But before we get too far with this, let's say what we're doing here because it definitely looks weird. It's a +4 estimate, and that part makes sense because here's the +4 in the denominator. It's as if we added 4 imaginary observations to our data. 2 of them are going to be considered successes. That's why we have +2 in the numerator, which means 2 of them are failures. But what the author doesn't really explain, I feel like, when you read through this chapter is, why would you want to do that? What does this even achieve for us? And to give just a really fast explanation, let's do something we don't typically do in class. Let's go to Desmos and plot out the situation. Once I get my windows working, give me a moment. Okay, that should do the job for us. So now, to understand the +4 estimator, first, what we actually want to go is take a look at the formula for the standard error right here, the p hat times 1 minus p hat. I mean, that really is a function. It's a polynomial function of degree 2. And so if you were to plot it, here's what it looks like. Y equals, let me see if I can put a p hat, maybe not. Let's just go with a p times 1 minus p. It's not quite the right plot because p hat, I'm putting it as p here just because I think that's a limitation for me. But p hat goes between 0 and 1, so we also want a domain. 0 less or equal to p, less or equal to 1. And that's the graph of the numerator inside the square root function. Now notice that this function is maximized right here. At 0.5, you get a maximum height, this location right here at 0.25. And so that's kind of secret of what's going on in these kinds of problems. For example, if our p hat is this one, 69, 339ths, we get the 0.0235. So we're about here. Let's see if I can target that well. 0.02, let's call that good enough. So at a 0.024, we get a 0.1624 altogether. But now what happens if we do a +4 estimate on it? We go 69 plus 2, 339 plus 4, and now note, it's just a little bit bigger. It's at a 0.207. So somehow, some way, we have a 0.207. It's now 0.1642, whereas, and this is kind of hard, 0.203, oh, I almost had it. 0.203, let's call it that, good. At a 0.204, we get a 0.1627, but now move to a 0.26, and it's increased to a 0.1624. The closer it gets to 0.5, the higher it's going to get to a 0.025. And that's all the +4 estimate is trying to do, widen out that part of the standard error. Does that make sense to folks on how that's happening? Okay, so if you add 2 successes and 2 failures to the numerator denominator, all it does is it moves your statistic closer to the center, making this larger. But if that gets larger, the widening happens right here, and it makes the whole confidence interval itself widen out. What's the effect of that? Well, if the conditions up here are not met, then 95% confidence is a lie. Yet we can correct it by just widening out the interval, and now this becomes a more accurate statement. It's conservative as well in the sense that if I use a +4 estimate here, I'll still state 95% confidence, but the confidence might be more like 95.5 or 96%. It might truly be a little bit higher. So we're being conservative when we say 95% confidence. So all that to say, this achieves a wider confidence interval as the effect, making us more honest when we go to say whichever level of confidence we were given. To use the full procedure, we just put P tilde right here. We use the same exact critical number Z star, but we're not using the standard error. We have to make this modification right here using the +4 estimate. So to me, I think this is the easiest part to miss. This is not the standard error SE. It's very, very similar, but the difference are you have P tilde here, and your denominator is using the new +4 sample size, so n+4 goes down below there. Everything else is similar, except the condition checking suddenly becomes way, way easier. And any questions at all then, folks, with how this procedure ought to go? Okay, well, let's practice it right away. It's kind of like a second example of doing a confidence interval because the change is really pretty small. It's just really here and here are the two changes on the estimate. So here's the data we'll take a look at for the +4 estimator. So this one has to do with medical technology, and it says the technology underlying hip replacements has changed as the operations have become more popular. They cite here that over 250,000 were done in 2008. Now they go to tell us, starting in 2003, highly durable ceramic hips were marketed, but unfortunately for too many patients, even though had higher durability, they were counterbalanced by an increased incidence of squeaking. So people had all these fancy, very durable hips, but grandma was squeaking in the grocery store, and that can really kind of be devastating in all honesty. And so this was a problem that suddenly had a lot of interest. And I think that was like almost a pun right there because of hip replacement, but who knows? The actual study says in May 11th, 2008. So these hips have been on the market for a while. I do want to mention right here, medical technology problems are extremely hard to analyze because when we go to now write our conclusions, we have to think of the technology as it was and as the training was for using this technology in 2008, but all that stuff starts to evolve, the technology and the training on how it's implemented. But in this year here, in the New York Times, they reported that there's a study of 143 individuals. It's just right here, just to emphasize, we have a sample size, who did have ceramic hips between the years, 2003, 2005, got that date wrong. So this is when the technology was still pretty new, looks like. 10 of the hips developed squeaking, and that's what we would consider a success in this problem. We're interested in the not great outcome, so X would be 10 successes. So that's the analysis of our problem, and part A asks us, explain why the conditions for the large sample confidence interval are not met. Any volunteers for what goes wrong just immediately with these data? Exactly. From this alone, we're just completely stopped from analyzing the data as a confidence interval. So we'll just say right here, since the number of successes is less than 15, the conditions for that particular interval, I'll just say that interval, are not met. They could have made that method work, but the sample size of 143 individuals was not large enough, and pulling a whole new set of data just to get the right interval is not a good practice. They still want to analyze the data they have, so they might have went to this interval, the +4 confidence interval for the proportion. So let's now analyze this completely with a complete analysis. We'll choose our level of confidence as we go through and see what's going on with those hips. So first we want to state the practical question indicated that requires a statistical inference. There's no actual question directly being asked here, but you can always imply one. One could be, what estimate can we give for the percentage of, instead of saying ceramic hips that were, I don't know if the right word is installed or the procedure for them between 2003, 2005, I'll just say these hips, referring to these. What estimate can we give for the percentage of these ceramic hips that squeak? So to me, that would be the implied question in this problem right here. We're just trying to make an estimate. A hypothesis test usually does have a direct question that you're trying to analyze. Next thing we want to do is define that unknown parameter, but it goes just like in the last problem. We have categorical data with successes or failures, like we indicated right here to start. So P will be equal to the true proportion of these ceramic hips that squeak. Well, now we have to select the level of confidence, and I'll leave it up to the class. How confident should we be on our estimate of squeaking hips? Any volunteers for a confidence level on this one? Oh, we've got one in the chat. Let's go for 95. Good call, Hannah. Thank you for that. So we're going to estimate this with 95% confidence. So now we've got our parameter, we know what we're estimating and to what degree we're going to estimate it. But now, while we're using the +4 confidence interval, so we need to check the conditions. One of the conditions is already that your confidence level is above 90%. I would say, again, that's kind of skippable. We have never done a confidence interval below 90%. The major pertinent thing is the sample size. But that's the easiest part of the +4 estimate. The sample size n just had to exceed 10. So first thing I'd probably say is, since the sample size is 143, which is greater than or equal to 10, that's our benchmark for this analysis. The sample size is large enough. So the robustness condition in Spirit does pass. We have a large enough sample size to use this method. Next thing we wonder is, do we even have random data? It says here, the New York Times reported that in a study of 143 individuals who received ceramic hips, 10 of them squeaked, but there's no information at all about randomization. So we'll just say down here, it's not known if these data were from a random sample. Doesn't mean we will stop the procedure because we don't know about randomness, but it's something we have to mention when we get to our end of conclusion, that our conclusion may be challenged if it turns out the data were not random. But when it says check the conditions, usually we're mainly just trying to see, is the sample size large enough? So we have enough successes or just exceed 10 in this situation, or to overcome enough skew if the data was quantitative. So condition checking is actually pretty fast for categorical data. That's a bit refreshing, I'd say. Next thing to do is just crank out all of our results using the formulas above. First thing we want is, let's see here, we have x and n. So I'd probably start off by just calculating p tilde. So p tilde is our estimator. Let's put this one in green, or statistic. It's going to be x plus 2 divided by n plus 2, or excuse me, n plus 4 altogether. So our numerator is going to be 12. Our denominator is going to be 147. So we got P tilde out of the way. Maybe the next thing we can go for is critical number. At 95% confidence, Z star equals 1.9600. Then right after that, we can calculate standard error. Well, I shouldn't call it the standard error because it truly isn't one. Let's just write out this way. Square root P tilde times 1 minus P tilde over N. So we need to do a computation on this thing right here. Let's just focus on it for the moment. And then we'll put these three results all back together for the full interval. So at the moment, all the fighting is right here. And really, it's mostly fighting with calculator that happens for this. So in place of P tilde, it's 12, 147, then 1 minus the same quantity. Denominator is going to be the same. Oh, and I did make a mistake right there. Sorry about that omission. Should be a +4, but probably the better strategy is you're going to see some parallelism here. If you divide by 147 here, you probably have to do it right here. That's usually how I double check that everything just looks right. And that's the +4 in action for that denominator in that location. So without all that set up, we're back to the calculator. Just another relaxing square root, maybe not in all caps though, 12, 147. Hit the multiplication bullet if you're using RStudio. But I would say a good strategy here is definitely use the calculator that you intend to bring to the exam, since you'd want to be familiar with that one. Then multiply by 1 minus 12, 147. Then divide by 147. And I get for standard error, after all of that, 0.0, not standard error, but this quantity right here, 0.02258. 3 maybe. For these kinds of data, when it's categorical, one of the things I try to go for is a little bit more accuracy if I'm going to round anything at all, since at the end of the day, we're going for percentages, and that's already a decimal shift 2 places to the right. You often want to be just a little bit more precise for intermediate computations. I'd say 5 significant digits is a pretty good benchmark. Well, any questions, folks, with any of these 3 components that we calculated so far? Okay, well, we're just about there. We'll put P tilde, add or subtract, Z star, multiplied by, I won't call it a standard error again, this formula, P tilde, 1 minus P tilde over N plus 4. Altogether, this is going to be 12 147s. Add or subtract 1.9600 multiplying 0.022583. And let's put this on the next page to avoid that page break. So finally, we're going to have P in the middle, a lower bound and upper bound. So same kind of stuff as we've been doing essentially since chapter 14. And this is the new values we'll throw in. 12147 minus 1.9600 times 0.022583. So we have a lower bound of 0.0374. Okay, that looks about right. Then next one, convert this to a plus. And that's finally our upper bound. We've got a 0.1259. Well, we did it, folks. That's our second conference interval for the day. Any questions at all getting to that stage? And it says, if that equation isn't standard error, is there a name for it? You know, there's no specific name that was given for this thing. I guess probably the best name you could give it is standard error for the +4 estimate. So I'd say this would be a good shorthand for it. SE P tilde. I avoided that mainly because our author doesn't discuss this as a standard error whatsoever, so it felt like just a weird thing to mention. But I'd say that's a pretty important, pretty okay terminology for what we've been doing so far through the course. It's the modified standard error and modified modifications because of P tilde there. Other questions about that or other things so far? Okay, well, we need to give a practical interpretation, but this is almost automatic at this point. It's extremely formulaic at this point in the semester. I'll start by saying with 95% confidence, if we use the large sample confidence interval, this is the part that would have been the lie right here. But because we have widened out our interval, we are now a little bit more honest when we say this part, 95% confidence. We go over here and you can call it the true percentage or the true proportion, always up to you. To emphasize that, I'll keep this one as true proportion. The true proportion of these ceramic hips, you could say that developed squeaking, or you could be a little bit more terse and just say that squeak. Because I said proportion, I'll just keep the numbers in this format rather than 3.74% is between 0.0374 and 0.1259. Well, we did, folks. That's the analysis of this squeaking hips problem. Definitely more recent data, at least. So this one, I feel like, is pretty important as a problem. But any questions at all, folks, with our analysis on this one? Okay, so analyzing confidence intervals for categorical data, it should feel very, very similar to what you did in chapter 14, chapter 17. The only change is we're talking about proportions, or you could have called them percentages, and slightly different modifications to our methods. But now one thing that does happen is if we're doing a hypothesis test, it feels suddenly a lot different than what we've done in chapters, say, 14, 17, or 18. The reason for that is all because of the central limit theorem. We mentioned this before, but let's highlight this again. The central limit theorem for proportions is unusual when you compare it against the one for means. Let's take a really fast look. In the one for means, this is a two-parameter description right here. You have to specify the location value, mu, and the shape value, sigma, right here, in order to get a full description for your central limit theorem. That's whenever you're looking at sampling distribution of the statistic x bar. But like we said, there is only one parameter of interest when we're dealing with categorical data. And so now, if you're doing a hypothesis test, well, the very first thing you do in a hypothesis test is you assume that the null hypothesis is the reality of your actual data. In other words, you're going to assume that's true right there immediately. If you are assuming that this is true, well, you have assumed a value here, here, and here. Let's emphasize where it really, really matters. So this time we are absolutely not using the standard error. We are using the exact standard deviation of the problem the moment you're doing a hypothesis test. We'll assume that that's the real value of the statistic and just see how compatible our data is with that statement there. Because of that, another thing that's going to happen is our conditions are checked relative to the sample size of 10. In fact, when we did the central limit theorem, that's how we determined whether we had reliability, whether the sample size was large enough for this approximation right here to be a decent one, for it to be really well approximated by the normal distribution. We keep that there, and the only reason it was bumped up to 15 is because if you're doing a confidence interval, there is no null hypothesis like this, and you can't actually calculate this thing. You estimate it with the standard error, But now you have estimates on top of estimates, and to get reliability, we need to bump up the sample size. That's why it was set to 15 for confidence intervals, unless it was the +4 method. So back to this problem, it says, gather a simple random sample size 1024 from population with true proportion of successes P. We're going to assume immediately that P takes on a value 0.34. And if that null hypothesis is true, we can now say this. What is the sampling distribution of P hat? Well, by the central limit theorem for proportions, we have that P hat, our statistic, is distributed as, this is not the same tilde as before, this one is the actual symbol for is distributed as. Normally, we'll put in, for this location, the true value P, which is 0.35. Then in the second position, the standard deviation will be 0.35. 1 minus 0.35 divide by n. And, oh, I did make a mistake. We know the value of n, it's 1024. So let's actually put that in. And we could leave it just like this. If we were about to use this idea, we were using test statistic. This is just the denominator of the test statistic. It's almost better in that form, so we can get a more accurate answer when we go to calculate the test statistic in just one shot. There's no extra approximations. So the big gist of this problem is when H naught is true, which we always assume true as the very first step in hypothesis testing, the exact value root P, 1 minus P, divided by N, is known. And to go off a comment that Hannah was mentioning, this one would have a nice formula for it, or not quite formula, but symbol. This would be referred to as sigma, because it's a standard deviation, and it's a standard deviation relative to the statistic P hat. So that's a pretty standard symbol for this right here. Let's also mention it. Sigma P hat is this value. So 2 changes if we're doing a hypothesis test. Again, we throw away the standard error, we never needed it, and our conditions also check, or excuse me, also change in a major way. Any questions so far, folks, with what we have to this stage? Okay, well, let's take a look at the full procedure. In the significance test for a proportion, like before, we're going to have a null hypothesis, P equals P naught, like we saw before. This P naught value is something stated in the problem that we have to identify, even to state our hypotheses. And same comments like we mentioned before. We won't have to mention these each and every time, so I'll just point that in and say, this is something that we'll just briefly discuss, what we know about randomization or what we may not know about it. Down below right here, this is the one we'll carefully check. And why not? Let's just mention it here just to be specific. And now that we're mentioning we should carefully check this one, note the way it's done. We're not looking for successes and failures in the sample. Not at all. There could be no successes in the sample, yet the conditions still pass. The reason for that is we're just checking how compatible our data is with the statements right here from the null hypothesis. So if we make that null hypothesis a statement we regard as true, we just say, how many successes do we expect when the null hypothesis is true? That's this one right here. And how many successes do we, or excuse me, failures do we expect? That'd be this formula right here. These are almost always going to be non-integer values, so they'll have to be rounded and such, but they don't have to be rounded to the nearest integer. And they just have to be at least 10. Then, same condition as before, your sample size, if it did exceed 10% of the population size, causes a problem with this method right here. We lose independence from the binomial distribution. And so this is something that is true for all of our problems, but something to be mindful of as well. So with all that, I'd say the trickiest thing is right here. Condition checking is a little bit different than we'd expect. This is going to carry over to the next chapters as well. And our test statistic goes like this. Whatever value you assumed right here for the null hypothesis, we calculate the difference right here. So now this is going to calculate the exact standard deviations. Here's the standard deviation part, that your statistic, p hat, is away from the statement of the null hypothesis value. If that's really large, then that starts to say the null hypothesis was the problem and we ought to reject it. But if this is a small value, we'll fail to reject it. And really, what we're doing right here is just kind of reviewing hypothesis testing as we saw it in chapter 14. This could have been our very first method. Well, aside from that, because this is kind of a review in a certain sense, I felt like it might be a good idea to fill out this table again. Might be a little bit redundant, so I'll leave it up to the class. Does that seem like a good thing to do next, or would folks like to skip it? So I'm saying, class, that this would be a good one to hit. Okay, let's run through this as well. It's a good review, I'd say, and we're going to calculate p-values. This could be your place to return to. First, we're calling this the test statistic z, and it's going to be distributed normally. Z indicates the standard normal distribution with the mean 0, standard deviation of 1. And here's what the test will look like. If it's a right tail test, then you're probably looking at a picture that's about like this. This is N01, which means we have 0 down here. And the test statistic Z, let's use a different color for that just to make it stand out. For a right tail test, you hope it's over here. This will make it look significant, like you're really rejecting the null hypothesis. But it could be way out here. Your p-value is like 0.8 at that case. I'll draw it this way, just sort of generically. So here's Z. Your p-value is this area right here. And so that means the p-value will be equal to p norm Z lower dot tail set false. And that does the job for us on the right tail test. Pretty much the same picture over here. We just flip it around across 0, and it looks like this. Let me try again with that curve, though. That'll do. So here's N01. It's not my best work, but does not have to be perfect. So here's 0 in this case. Over here, for that test statistic, this would look like it's going to fail to reject the null hypothesis. That area looks bigger than 5% or 10%. If it looks like this, here you probably would reject the null hypothesis. That p-value is probably something like 0.3, the way it's plotted. So in this case, the p-value would just be p norm Z and nothing else. So that's what gives us this area right here. And the hardest one to specify, but also the most important one, because this one is the default test, is this two-tailed test. It's tricky to specify because your test statistic Z could either come out as positive or negative. So if Z is positive, you might have a picture that looks more like this one. I'll just draw just a really fast curve without the N01. Let's put a 0 there. Always good to orient yourself. So let's say our Z is right here. Now you can write down one overall formula that handles both positive and negatives all at once. I think a lot of people, when you go to calculate this, you're probably just going to split off into two different cases. If it's positive, then p-value is like doing the right tail test. But don't forget this part. Let's emphasize it. Your p-value is always double as large as your right tail test or your left tail test. In a certain sense, that's kind of nice. That minimizes type 1 error. It'll be 2 times p norm Z with lower dot tail set false. So that's our positive situation. Next, if z is negative, our picture looks about the same, looks like a left tail test. So here's z right here. But we have to double that area. So it's going to be p-value equals 2 times p-norm z. I'm looking at my two graphs for the two-tailed test. I feel like it's not quite right. It did say to double that area, but that means when you're doing a two-tailed test, you're also using this area. I think this is a good addition to the graph, just to conceptualize it well. The two-tailed test allows for z to be either at this extreme positive or at this extreme in the negative region. Likewise over here, the reason we're doubling the area is because we're trying to find both of those extreme possibilities, whether it was that large extreme negative or that large extreme positive. It's more about the distance away from zero, and we take both tails into account. Well, we got it, folks. That's the full description of how to get every one of our p-values. Any questions at all building that table? Okay, well, we've done lots of good work so far, and here's our next problem for the day. This one is from the Pediatrics Journal in, well, I don't have an actual date on this one. It looks like some pretty tough to analyze data, but let's see if we can make a start to this one. And I won't try to go right to the minute. We'll look for a natural stopping point on this one. Maybe we'll stop here on defining the parameter. That'll be a good time to refresh ourselves on Wednesday's class. But here's how this problem starts. It says, in the article, prothrombotic factors in children with stroke or encephalopathy, these people compare differences and similarities in children with arterial ischemic stroke and porencephaly. I'm probably pronouncing a lot of these weird. But when they say in these children, looks like that's the population we're thinking about. So we'll need to remember that to define the parameter. Now they tell us there were 3 classification categories used. That's a red flag right away if you're reading this data and expecting to use the methods that we're using, because our methods require 2 categories, successes and failures. So let's keep on reading. This actually fits the bill, but let's see why. 3 classifications were used: perinatal stroke, delayed perinatal stroke, and childhood stroke. It says of the 59 children, 25 were diagnosed with delayed perinatal stroke. So there's 3 categories, and 25 of the 59 children were in one of those categories. Maybe highlight this as well. Now they go on to ask, do the data provide sufficient statistical evidence to conclude that delayed perinatal stroke does not compromise 1/3 of the cases among the 3 categories? So now that question right there is what allows us to actually analyze the data in the way we expect in chapter 19, in other words. Because look at what they've done. They've now said delayed perinatal stroke is the thing that we are focusing on this problem. That's the success. So we could come down here and say X equals 25 children in that category, so 25 successes. And the other 2 categories are just going to be lumped together into the failures category. So we have 25 successes, that was supposed to be an S right there, and the sample size is 59. So we're going to answer this practical question right here using, let's say, complete analysis and a hypothesis test. It says at the 1% significance level, so it'd probably be a good idea to just write that out. Alpha equals 0.01, just as a reminder. Well, that's the start of the problem so far. And when it comes to stating these questions, again, you could put it in your own words, that's encouraged. Or just as well, honestly, you could, if you find a portion of the problem that says it, and you do literally this, copy and paste it in, probably put it in quotes to say, we found the practical question of the problem and we've extracted it. then that's always completely fine as well. I usually give this just 1 point out of the whole process. That's just a way for me to know that you know this is what we're driving for and that problem. Well, any questions, folks, to this stage of the process? Okay, well, we've got about 4 minutes. We really rushed through this. We could define the parameter, the null alternative hypothesis. Some folks probably have done some of that work already. If you want to continue through this problem, I'd say go for it. But I think this will be a good stopping point for us. We'll come back, carefully work through this. If you did work a little bit ahead, you can compare the results of what we did. Before we call it a night, any questions at all, folks, with what we've done so far? Okay, well, have a great day, folks. Now, Wednesday's class, we'll finish off these notes here. We'll then move into chapter 20. We might get a pretty good start, do maybe one of the methods, a confidence interval method. And then after that, we're going to be changing gears and reviewing for exam 3 on Monday's class a week from today, chapter 17, 18, and this chapter here, 19. But have a great night, folks. I'll see you all on Wednesday's class. Yep, have a good one. Thanks, folks.